This chapter is about normal probability distributions, and we begin with the standard normal distribution. The probabilities assigned to a continuous random variable, like time, heights, distances, measurements, etc., cannot be listed. So they're usually shown in a graph. And the graph of a probability distribution for a continuous random variable is called a probability density curve. Probability density curve. Now, the continuous probability density curve must satisfy the following properties. Number one, the total area under the curve, must equal 1. And then number two, the entire curve must be greater than or equal to 0. In other words, the curve cannot fall below the horizontal or x-axis. So in other words, a function is never negative. So first let's talk about the uniform distribution. So a continuous random variable has a so-called uniform distribution if its values are spread evenly over the range of probabilities. Spread evenly over the range of probabilities. Okay, so let's look at some examples. And the first one is that the waiting time for a subway at a subway station. So it says that the waiting times at a subway station range from 0 to 8 minutes according to a uniform distribution. Okay, so here's from 0 to 8 minutes. And so we can just draw a horizontal line, because we are told it's a uniform distribution. Okay, so just like this. So there will be an example of a uniform distribution. Okay. Now, because the total area under the density curve is equal to 1, the area under the curve corresponds to the probability assigned to the random variable. So this whole area is equal to 1. So in other words, that is the probability assigned to the random variable. And since the area is 1, so length times width equals 1. And since we know the width, or if we call this the length, so it's 8 times w equals 1. Then we know that the width is equal to 1/8. So in other words, this would be 1 divided by 8. That makes the whole area equal to 1. So the height would have to be 1/8 for the area to equal, under the curve, equal to 1. Now here's a question. Find the probability that the waiting time at the subway station is 3 minutes or more. Shade the corresponding area under the curve and then compute its area, length times width. Okay, so let's do that. So the wait time is greater than 3 minutes, so that's between 2 and 4. So that would be this one here. So let's shade in the area under consideration. So the question is, what is this area here? What is that area equal to? So the probability that P of x is greater than 3 is a shaded area under the curve. So shaded area under the curve. Okay. By the way, this is where x is distributed uniformly from x equals 0 to x equals 8. So this wavy sign means it's distributed, in this case, uniformly. So then, numerically speaking, that means length times width, and the length is from 3 to 8. In other words, 8 minus 3 is 5. And we know that the width is equal to, excuse me, the width is equal to 1/8. We discussed it further up here, 1/8. So in other words, that equals 5/8 or 0.625. This is the probability that the waiting time at the subway station is 3 minutes or more. Let's look at another example. The position of the second hand on a clock face is uniformly distributed from 0 to 60 seconds. So in other words, it's the same situation before. We simply draw a horizontal line to indicate that the distribution is uniform. So that's our uniform distribution. And so if this is a length, we know the length is equal to 60. And so the width, we don't know, but we know that the product of length times width equals 1. The area has to equal 1. So therefore we can say that the width is equal to 1/60th, 1 divided by 60. So the height would have to be 1 divided by 60. And this way the area under the curve is equal to 1. So the question is, find the probability that the second hand will be anywhere between 10 seconds and 30 seconds past the top of the clock when you happen to look at the clock face. Shade the corresponding area under the curve, then compute the area. So between 10 seconds and 30 seconds, 30 being here, so in other words, the question is, what is this area here? So this is the probability we're looking for. So what is that equal to? Well, we know that this distance here is 30 minus 10, or 20. So the probability that x is between 10 and 30 inclusive is then equal to the shaded area under the curve that we just shaded in here. And so it would be 20. And we know that the height is 1 over 60. So that would be equal to 1/3 or equal to 0.333. So as you can see, computing the probability for a uniform distribution is really pretty straightforward. So here you have two examples that show you exactly how to do it. Next, we're going to talk about normal distribution. So here's a definition. If a continuous random variable is said to be normally distributed, this means the probability density curve is bell-shaped and symmetric. This shape is called the normal probability, distribution. Or simply the normal curve. So these two terms are interchangeably used, the normal probability distribution or simply the normal curve. And so when we say x is normally distributed with a mean of mu and a standard deviation of sigma, so this Wavy signal means it's distributed according to. So the normal distribution has the following properties. The normal curve is symmetric, well, it's bell-shaped. What you said, that is bell-shaped. And symmetric about the mean. And that means mu, the mean mu. Okay. Also, as the graph extends toward plus or minus infinity, it approaches the x-axis asymptotically. In other words, like an asymptote. That means that the graph gets closer and closer to the x-axis, gets closer and closer to the x-axis. But never touches it. You may have heard about asymptotes when you were in high school and you studied hyperbolas. Hyperbolas have asymptotes, so maybe in the context of that you may remember that what an asymptote means. It's a line that a curve approaches but doesn't reach. Okay, so the graph has what's called inflection points. Inflection points. Hope I can get that in. And that is where the curve changes from concave down to concave up at the end. Okay? So, and the distance from the center to the inflection point is simply the standard deviation sigma. And again, the total area under the curve is equal to 1 or 100%. And the area to the right of mu, the mean, is equal to the area to the left of the mean, and they both are 1/2 or 50%. So when we look at the standard normal curve, it is drawn with 0 at the mean, and a standard deviation of 1. So symbolically, mu equals 0, and the standard deviation equals 1. And of course, the total area under the density curve equals 1. Okay, so now we talked about z-scores a while ago, but z-scores follow the standard normal distribution with a mean of 0 and a standard deviation of 1. So z-scores and remember what a z-score is. The z-score tells you if a data value is above or below the mean, and by how many standard deviations it is below or above the mean. That was a z-score. Okay. So to find the standard normal probabilities, we draw a normal curve and shade the area of interest, and then we use technology or a table, A2, and that's, I'll show you what that looks like, to find the probability area for each z-score. So these z-score tables for standard normal distributions, you can find them anywhere. You can print one out from the internet and just look for that for the standard normal distribution, z-score tables, and there are two of them. One is for the positive z-scores, and one is for the negative z-scores. And if you use technology, a StatCrunch, or maybe a handheld calculator, like a TI-84 or something similar, then you can look up the z-scores very easily. But it's helpful also to use a table from time to time just to see how that works. So, speaking of tables, you see it right here. Here's a table. And here we have, let's say, a z-score of 1.3. So we go to 1 here, and then for the hundredths we go to 0.03. So this is a z-score for 1.03. 1.3 rather, 0.13. So what this represents is the area under the curve, to the left of it. So 0.13 might be here, and then the area under the curve would be everything to the left. Okay, so here's 0.13, and the area to the left would be equal to 0.5517. 0.5517, and that is the probability associated with a z-score. So let's look at the example where we asked to find the probability that the z-score is between -1 and +1. So what that means graphically, say 1 is here, and -1 is there, -1 and 1. So we draw a line here, a vertical line there. And what we're asked now is to find this area here. That's the probability that P is between -1 and 1. Z is between -1 and 1. Now, we need to look up the z-score for 1, and that will give us all the area to the left of 1. And then we need to look up the z-score of -1, and that's all the area to the left of -1. So we need to subtract the smaller area from the larger area. So let me show you in the z-score table what that looks like. So the z-score of 1 is equal to 0.8413. So 0.8413. So 0.8413. That's the area 13. That is the area to the left of 1. Now the smaller area to the left of -1, we look at the other z-score table for the negative z-scores. And so here the z-score of -1 is equal to 0.1587. So 0.1587 is the z-score, 0.1587, 0.1587. So we need to subtract that from the larger area, and that is equal to 0.6827, and that is our answer. So 0.6827. Of course, when you use technology, StatCrunch or TI-84 or similar calculators, you just simply input the numbers and out comes the answer. Okay, so just make sure you understand what I showed you here. And so whether you have tables or whether you use technology, you should be able to find the probabilities. And similarly, if we do a similar example for the probability of the z-score being between -2 and +2, look up the z-score for 2, look up the z-score for -2, subtract the smaller area from the larger area, and your answer should be 0.9545. 0.9545. Okay? Another example here, we'll find the probabilities that z is between -1.25 and 1.17. So let me use the tables one more time, and that'll be the last time I'll show you how to do it. But 1.17 would be 1.1, then we go over to 7, and that is 0.8790. So 0.8790. And now we need to look up the z-score for -1.25. So -1.25, we look up the z-score. And so we have -1.2, and -1.25 would be 0.1056. 0.1056. So now we subtract the smaller value from the larger value, and then the answer is 0.7734. So that is the probability, 0.7734. And again, if you use technology, you don't need the tables. but this was the last example I gave you with the z-score tables, so you have an opportunity to use that if that ever becomes necessary. And again, looking at the other probabilities, the probability that z is less than or equal to 1.45. Again, technology will give us an instant answer. And so let me just do that. So that would be 0.07, 0.0735. And again, you can use tables or use technology. And then the greater than probabilities, what's the probability that z is greater than minus 1.24? So minus 1.24 would be maybe here, minus 1.24. So we are looking for this probability here. So again, technology gives the answer right away. If you do it manually, you compute the z-score, the probability for the smaller area here. In other words, what's to the left of that, subtract it from 1, and that'll give you the area as 0.8925. Let me just fill in the areas that we did here. So minus 1.45, that might be about here. So minus 1.45, so this is the area we're looking for here. That's equal to 0.0735. Again, the probability is area. And let me just complete this one up here also. So minus 1.25, be about here. And 1.17, maybe about here. So 1.17 minus 1.25. And the area we're looking for is this here, and that is 0.7734. Remember that the probability is an area in this context. Next, let's look at a real-world example about bone density. A bone mineral density test can be helpful in identifying the presence of osteoporosis. The result of the test is commonly measured as a z-score, which has a normal distribution with a mean of 0 and a standard deviation of 1. So in other words, here the random variable x, the bone density reading is a z-score distribution. So x is normally distributed, normal, with a mean of 0 and a standard deviation of 1. Okay, so now we are asked, a randomly selected adult undergoes a bone density test. Find the probability that the result is a reading less than 1.27. So we know that 0 is here, so 1.27 might be right here. So what we are asked then is to find the area under the curve up to this point. So that's the area. So you can look it up in the tables. 1.27 for z-score, what's the corresponding the associated probability, or when you use technology, you find that the probability of x being less than 1.27, remember it's a randomly selected person, would be 0.8980. And I would encourage you to look it up yourself, again with technology or using a table. So using the same bone density test, in other words with a mean of 0 and a standard deviation of 1, find the probability that a randomly selected person has a result above -1, which is considered the normal range of bone density readings. So what are being asked to do? Well, -1 would be here, -1.0. So we draw a vertical line, and so we are looking for this area here. Again, with technology, the probability that x is greater than -1. When using technology or a table, well, when you use technology, it's very simple. Out comes the answer as 0.8413. That's the associated probability here. But if you use a table, what you have to do is you look up the corresponding area to z of -1. That gives a little area. And you need to subtract that from 1. And that'll give you the area to the right. Okay, so I would encourage you to try that out, and that you have some confidence that you can use tables. The next question is this. A bone density reading between -1 and -2.50 indicates the subject has osteoporosis. Find this probability. So we know -1 is here. -1 is here. And -2.5 might be right here. So we are asked to find this area here. And again, so -2.5 and -1.0. Okay. So again, using technology, you come up with the answer, the probability that x is between -2.5 and -1. Would then come up as 0.1524, about 15% in other words. If you use tables, you look up the z-score as the area for z of -1, and you look up the area for z of -2.5, and subtract the smaller area from the larger area, which gives you the difference between the two lines, and that should come out to 0.1524. So we know how to find the probability when we have a given z-score, whether you use technology or the tables. Now, in the opposite way, the reverse would be, given a z-value on the horizontal axis, find the probability area under the curve. So in other words, so now we have the given z-value. In other words, we know the area. Now we need to find out what the z-score is. And so let's look at a couple of examples here. What z-score separates the bottom 20% from the top 80% of z-scores? Okay, so let's look at that. So in other words, what we're looking at here is the 20%. We got here. Let me make a little line here. Now remember, now we're starting with the area. So this area here represents 20%. And then obviously the rest would be 80%. And so so if you use a table for that, we're looking for the area of 0.20, and even though we don't have an exact value for that, it's 0.2005, that's close enough. And so the corresponding z-score would be minus 0.8, and when we go up here, it is minus 0.84. So there would be the corresponding z-score, minus 0.84. So minus 0.84. That'll be the corresponding z-score. That, the z-score corresponding to the area to the left being 20%. Similarly, what is the z-score at p sub 95, the 95th percentile? Well, it's the same thing. We look for the area here under the curve. That is 95%. In other words, we want this area here to the left. We want this to be 95%. So when we look at the table, or we use technology, so this is 95%. And so that would be 1.645. 1.645. Okay. And one more example about the bone density. So using the same bone density test, find the bone density scores that separates the bottom 2.5% and find the score that separates the top 2.5%. So in other words, we are looking for the z-score that corresponds to an area of 2.5% and 2.5% here. So this area here, this little area here is 2.5%, and this little area here is 2.5% also. So when we look up the corresponding z-scores, we find that is minus 1.96, and it's symmetrical, so it'd be 1.96 on this one here, 1.96. And this is minus 1.96. And be sure to look it up yourself, or again use technology, either way. But just make sure you understand how these numbers come about.